In this lesson, we are going to begin to look at velocity and eventually we'll be looking at acceleration. So just a reminder of what velocity is. Velocity is the rate of change of position over an interval of time. So sometimes we use velocity in terms of s. So s meaning displacement. So s of t over, so the change in displacement over the change in time is going to give us velocity. I don't think we need that t there. Let's just erase that t. So the change in displacement or position over the change in time. The difference between velocity and speed is the velocity is how fast it is moving and in the direction that is moving. So it is a vector quantity. Speed is just the magnitude. So it's just the absolute value of the velocity, but it does not distinguish direction. So it is a scalar quantity. So that's the difference between velocity and speed. Okay, so here's an example of a rock that is being tossed from a bridge. The height function is given. So sometimes it'll give this height or s as displacement. So first of all, it wants us to find the instantaneous velocity at 1 second. So if the position or the height is given, the instantaneous velocity is going to be the change in height, or h prime of t. So h prime of t we can also call velocity, and in this case, let's call this a. In this case it will be negative 9.8 t plus 12, and we want to find that velocity at 1 second. So we'll do velocity at 1 second, and it will be 2.2 meters per second. And since it is a positive value, that tells us that it is traveling upward. So think of the path of the rock as going up and down. Because my velocity is positive, it means that it has a positive slope, right? So h prime of t is the slope of the tangent at a specific point. So since it is positive, it tells me it's increasing and it is traveling upward. B says, what is the velocity when the rock enters the water? So in order to determine when it enters the water, we will need to solve for height when height is 0. Because we can't find the velocity until we know at what time it hits that water. So we'll substitute in 0 for height. And then we will use the quadratic formula to solve for x, since it's not factorable. So we'll just plug these numbers into the quadratic formula. And when we calculate this, x has two values. One is a negative value, which is not possible because we can't have negative time. And the second value is positive, 3.36 seconds. So that is the time at which it hits the water. So at this point, we want to find velocity at 3.36 seconds. And we'll add 12, and that works out to be negative 20.9 meters per second. So that tells us that since it's negative, it is traveling downward, which makes sense because if we go back to our diagram, here's where it's going to hit the water and it's traveling down at that point. So that's why the velocity is negative. The next question, what is the initial velocity? So that's just at time 0. So velocity at 0 is just going to be 12 meters per second. So again, it's positive, meaning it goes up first. And then finally, D says, when is the rock at its maximum height? So it would be at its maximum height. Let's go back to the diagram. So it would be at its maximum height when velocity is 0, right? The tangent line at that point would be a horizontal line. So velocity would be 0. And so we'll put in 0 for velocity and we'll solve for time. So t works out to be 1.22 seconds. Okay, so that is a basic velocity question. And here is the graph that goes along with it. So there's lots of information we can see. We can see the initial height was at 15 meters. We can see that the velocity is positive as we reach the maximum, where it is now negative. And then here, or 0, sorry, horizontal line. And then here the velocity changes to a negative velocity. The impact of the water was at minus 21 meters per second because it's going down, and that occurred at 3.36 seconds. So that is our diagram of the height of the rock. Okay, sometimes you might have a particle that's just moving in a straight line. So the displacement is given as s of t, and the first thing it wants us to figure out is the initial position. So an initial position would be at time 0. And that would work out to be 0 meters. Secondly, it wants us to determine the velocity at 2 seconds. So in order to do the velocity, we need to find the derivative of the displacement. So s prime of t, which we can say is the velocity. And so it will be 9t squared minus 81t plus 162. Once we have that equation of the velocity, we can then sub in 2 seconds to find the velocity at that point. And that works out to be 36 meters per second. So it is moving in the positive direction. When is the object stationary? Well, the object is stationary when the velocity is 0. So we're going to take our velocity equation and we'll sub in 0 for velocity, and we're going to solve for t. So 9 is common. Let's take that out. And then we can factor that trinomial. It is a simple trinomial. It would be minus 6 times minus 3. So time is 6 and time is 3. So at 6 seconds and 3 seconds, the object is stopped. When is the object advancing and retreating? So this means when is it going this way, advancing, and when is it going this way, retreating. So in order to figure that out, I'm going to make an interval table to determine using my velocity equation. So I want to know at time 0 to time 3, let's use t. At 3 seconds it stops, so what's it doing in between? Then from 3 seconds to 6 seconds, what is it doing there? And then greater than 6. So we'll put in our factors here. And then we'll look at the velocity, and we're looking at whether it's positive or negative. So 9 is always positive. We have negative, negative, so that's a positive. So that means that at this interval it is advancing. We have a positive result. In the next interval it is negative, so it is retreating. It's going in the reverse direction. And then in the last interval it is positive, so it is then advancing. And then the final question is determine the total distance traveled during the first 8 seconds. So this is what I know. I know at 0 to 3 seconds, it's going in that direction. I know from 3 to 6, it's going in that direction. And then I know from 6 to, and it wants 8, so let's just put 8, it's going in that direction. So I have to figure out the distance it's traveled over each interval. So I'm going to organize it into a table. So I want to know the displacement at 0, the displacement at 3, the displacement at 6, and the displacement at 8. Where is it located in those 4 values? So we know S of 0 is 0. S of 3, if you plug it into the displacement equation, you get 202.5, 162, and 240. So you can organize it in a table if you want, or you can just look at it on the diagram. So I'm looking at these times at 0, and then I want to know where it is when it stopped, and then when it ends at 8. I'm looking at the displacement, which we just calculated. And then I want to find the distance it's traveled over each interval. So between here and here, so when it started at 0 and stopped at 3, it traveled 202.5 meters. Between 6 seconds and 3 seconds, it traveled in the opposite direction, 40.5 meters. And then in the last bit, it traveled 78. So you want the absolute value, right? You want the distance it's traveled. So the total distance traveled is 202 plus 40.5 plus 78. So that works out to be 321 meters. So on my diagram, it traveled 202.5 in the first bit, then it went backwards 40.5, and then it went forwards 78. And then we're just adding that up. Okay, so what can we use derivatives for? We can use them to solve lots of different types of problems and applications. We can use it for population size. We can use it in economics and finance. So we'll be looking at cost, revenue, profit. We can look at volume, maximizing, minimizing volume, things like that, area. So lots of different applications that we can use. Okay, let's look at one last example here. So this is similar to what we just did. Make this up a bit. Okay, so we have a flare launched. We have the height given, the initial height, or sorry, the initial velocity. So we need to find the velocity, which will be the derivative of height. So we'll call that v of t. So that works out to be minus 9.8 t plus 16. Once we know the velocity equation, we can find the velocity at 0, which is obviously 16 meters per second, which means it's going up. Question B says, what is the height at launch? So that's just the height at the beginning. So h of 0 is going to be 200 meters. How fast is the flare descending at 6 seconds? So again, we'll use our velocity equation at 6 seconds, and we'll just put in 6 for time. And that works out to be minus 42.8 meters per second, which means it's traveling downwards at that point. D says, when does the flare hit the water? So again, we'll have to use our quadratic formula to determine this, because we want to know at what time it hits the ground first. So we'll figure that out. And so we get two values for x. We get minus 4.96 seconds, which doesn't make sense because we can't have minus time. And we get 8.23 seconds. So that's the time that it hits the water. And so we'll find the velocity at that time for part E. Part E says, what is the velocity when it hits the water? So we'll sub that into our equation, and we get minus 64.6 meters per second, again, which means it's traveling downward as it hits the water.